Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering. Previously we discussed the stress strain curve of metallic materials. In this video we are going to extend our discussion a bit and we will categorize different, especially metallic materials according to their different nature depending upon their stress strain curve. So basically we will have three main categories: ductile materials, brittle materials and malleable materials. So simply we will try to understand how we can determine whether a particular metallic material it is ductile, brittle or malleable. So before that, a quick review of the basic concepts which we have covered. So stress strain relationship, which is basically given by Hooke's law, which states that the strain produced, whether it is longitudinal, volumetric or shear, that is bending angle, it is directly proportional to the applied stress. Now it can take different forms with different proportionality constant values within the elastic limit. Okay, in the elastic limit is the maximum stress which the material can withstand without permanent deformation. That is, if the stress is removed, it returns back to its original shape and size. Now that relationship between stress and strain, that gives us the constant, the proportionality constant, which is the modulus of elasticity. It has different forms: Young's modulus for length, bulk modulus for volume, shear or rigidity modulus for bending angle. Also we discussed the stress strain curve, which takes us beyond the elastic point, okay, which is this. So please watch the previous video first, because here I will not be going into detail about all of these things, because we have already covered in detail these things in the previous video, stress strain curve of metallic materials. So why metallic materials again? Because only with metallic materials we can get the full range of values, full range of points, full extension of the stress strain curve. Other non-metallic materials cannot withstand such higher levels of stress. They will not go through all of the full range of points here. So again, basically it is the journey of the material from elastic region to plastic region, temporary deformation to permanent deformation. Now the nature of the stress strain graph can give us a lot of information about the basic nature of the material. Now basically the three categories which we are discussing here: ductility, brittle and malleability. Ductility is the ability of the metal to be drawn into thin wires. So it means much larger increase in strain. Okay, ductility, with the application of load, with the application of stress. Okay, it is the ability of the the metal to be drawn into thin wires. I am saying metal because mostly metals exhibit ductile properties. So they have large plastic range of extension. Beyond the elastic limit, they have large plastic extension. One major characteristic of ductile material is that the gap between the elastic point, okay, elastic point, remember, it is the point of up to which there is temporary deformation only, the maximum stress which the metal can withstand without permanent deformation. And fracture point is the point where it snaps, it breaks. So the gap between elastic limit and fracture point, that is very, very large. It is widely separated, as you can see here. This is the elastic limit. This is the elastic limit. This is the fracture point. Such large gap between these two. This is the ideal stress strain curve of a ductile material, mostly metal. So I'm using material but still metal. It's metal which exhibit this property. So the gap between elastic and fracture point, it is the plastic region. This is the plastic region, if you remember. This is the plastic region behavior of the material. This is the elastic region. So if the plastic region is wide, points are widely separated between the elastic and plastic region, elastic and fracture point, then the material is ductile. It means it can withstand much higher levels of stress and the strain is large. Okay, so the materials, they undergo an irreversible increase in length before breaking, before fracture, before snapping. So they can be drawn into thin wires. Ductility is basically the ability of the metal to be drawn into thin wires. Thin wires means much larger increase in strain. Now commonly used ductile materials, they are copper, silver, gold, iron, aluminium, they are commonly used. So these are ductile materials. So they have large plastic range of extension and the fracture point is widely separated from the elastic point. This. Now brittle materials. Brittle materials, it is just the opposite. This is ductile. Brittle materials, it is just the opposite. They cannot withstand higher levels of stress. They cannot withstand. They cannot withstand. Even beyond the elastic limit, if we increase stress even by a small margin also, depending upon the characteristics, they will snap. It means their fracture point is very close to the elastic point. See here, the fracture point, this, and this is the elastic point. So it is very small, the gap is very small. As compared to the ductile materials, the gap is very small. So the fracture point is very close to the elastic point. So the plastic region is very small. Here the plastic region is small. Here the plastic region is large. Large plastic region. Okay, so brittle materials, they have small range of plastic extension. Okay, and these materials, they break as soon as the elastic limit is crossed. Okay, their breaking point, it lies close to their elastic limit. Example, cast iron, glass, ceramics, these kind of materials. Okay, another interesting way to observe is the area under the stress strain curve. See, if we take this, the mark a dotted line here, this entire area, this is the area under the stress strain curve. As you can see, the area under the stress strain curve for ductile materials is very large. Okay, the area, and here the area is much smaller. Much smaller area. Smaller area here. Here there is larger area. Okay, large area. So the area under the stress strain curve for ductile materials is high. The area under the stress strain curve for brittle materials is low. Okay, now is malleable materials, malleability. So malleability is basically the ability of the materials to be beaten down into thin sheets. Ductility is to be drawn into thin wires. Malleability is the ability to be beaten down into thin sheets. Okay, so here the thing is that when a solid, it is compressed, so here the volumetric stress comes into play, volumetric stress strain, and the the volumetric bulk modulus of elasticity, that comes into play. So here, when a solid is compressed, basically metals, a stage is reached where it cannot recover its original shape, like the elastic limit. Okay, beyond that it cannot recover back to its original shape. Now this is the elastic point of compression. Then beyond this, the solid behaves like a plastic body. Now, that point beyond which it cannot recover back to its original form, that is called as the crushing point. So this is for malleable materials, the stress strain curve. Again, here it is bulk stress and bulk strain, volumetric stress and volumetric strain. So this is the elastic limit beyond which there is plastic deformation. This is elastic region. Within this range, it can recover back to its original shape and size. But here, beyond this, this is the plastic region. It cannot go back to its original shape and size. Now, this is the crushing point where it can be turned into thin sheets. Okay. For example, if we take a material, we beat it down up to this level, let's say. Okay, this is the crushing point, beyond which it can again be beaten down to form thin sheets. Okay, this is called as the crushing point. Okay, the crushing point where it can be turned into thin sheets. Okay, the yield point which is obtained under compression, that is beating it down, that is called as the crushing point, and it is beyond the elastic limit. Okay, and after this stage the materials are said to be malleable, that is they can be hammered or rolled into thin sheets, as I said. So commonly used malleable metals, they are gold, silver and lead. Mostly these things are used by jewelers, gold and silver jewelers, to draw gold and silver into thin wires for making jewelry, or to thin sheets for different purposes. And if in some cases gold and silver, malleable sheets, gold and silver sheets, they're also used for decoration of sweets. It is also used also in various cases for various decoration purposes, especially jewelry. Gold, silver, it is drawn into thin wires, or it is beaten down into very small sheets. Okay, so these are the properties. So the main properties which are important for us for application purposes, it is ductility and malleability. Brittle nature is they cannot withstand higher levels of stress and they will snap just beyond their elastic limit. Ductile, they can withstand higher levels of stress beyond the elastic point and undergo large strain changes in length or dimension. Malleability, once the elastic point is crossed, they enter the plastic range, and up to a certain point where the crushing point is reached, where they can be turned into thin sheets. Okay, so this is the ductile, brittle and malleable properties of metals, especially metals, but other materials can also, other materials are basically brittle. They are brittle materials, ceramics, glass, they are brittle. Okay, mostly metals, they qualify for ductility and malleability. Okay, so here we have discussed.